Hi everyone. Today we are going to start chapter 3. Chapter 3 is going to deal with mostly linear equations of second order. And today we are going to do homogeneous equations with constant coefficients. Well, we are going to start with considering a linear differential equation of second order. What is linear differential equation of second order? Well, it looks usually like this. Second derivative y plus p of t first derivative plus q of t function equals g of t. So it's supposed to look like a polynomial of second order, like ax squared plus bx plus c, but instead of x we have like second derivative, first derivative, and kind of zero derivative function itself. Instead of abc we have functions. Usually we can divide over the coefficient of the second derivative the whole equation, considering that it's not equal to 0 anywhere, and turn it into like solved for second derivative form. This is right part. If right part is equal to 0, equation is becoming homogeneous. Let me write down. I'm going to write down x to the power of 0 actually. And over here kind of d, right? A, B, C, D. So A, that this coefficient, B is this coefficient, C is this coefficient, they all can be functions, and D can be a function too, right? So let me write down, if G of T is equal to 0, right side. Equation is called homogeneous. Well, guys, we just studied homogeneous equations when we were doing the previous section, right? Homogeneous equations and Bernoulli. This is different homogeneous. This is homogeneous about the right side. The equations we were studying, the homogeneous equations we were doing before, were homogeneous about a ratio y over x. So whenever you say homogeneous, that's actually homogeneous about something, right? Here we have homogeneous about the right side. Right side is equal to 0. Well, we're not going to consider actually any arbitrary coefficients. We're going to start in this section with constant coefficients. So if coefficients of this equation are constant and the right side is equal to 0, equation is going to look like this. Equation with constant coefficients. A y second derivative plus b y first derivative plus c y equals to 0. That's the simplest version of this equation, right? We just set up numbers for every coefficient instead of the function, right? We put 0 instead of the right side, and I added coefficient a in front of the second derivative. Normally, guys, you understand that you always can divide by a and get rid of this and get to this form. It's just like for generality. Okay, so I'm going to write down that A, B, and C, constant numbers, constant real numbers. Okay. And what else? Well, let's just write down example. Example, typical equation of second order. Second derivative minus y first derivative plus 2y equals to 0. Can be y of 0 equals 1, for example, and y prime of 0 equals 1. This is typical initial value problem with second order differential equation with constant coefficients. We are not going to solve this example right now. We are going to first kind of develop a method. How do we solve equations like this, and then solve something similar. Okay, so the question is how to solve. How to solve. Well, we are going to look for exponential solution. Seek for exponential solution. of the form y of t equals c e to the power of rt. C and r are undetermined constants, and we are going to look for a solution in this form, and eventually we are going to define these constants, of course. Now, question is, why do we look for a solution looking like this? Well, maybe we just can say we guess that that's gonna work. Maybe we can refer to equation of the first order. Imagine you have a first order equation. First order equation, something similar, something like this. Y prime equals a y. First order equation with constant coefficient, homogeneous, right? If you move everything to the right side, it's going to look like you just cover the second derivative. So if you have just the first derivative and the function, that's first order equation. What can be a solution? Well, this equation is not necessary to solve by special method. We can do separation of variables. Separate. So separation of variables, dy over y, I'm moving this y to the left side, is a dt, right? Integrating both sides is going to produce for us a ln of y equals at, right, plus a constant. And here a is just parameter of the equation. It's like b or c. Usually it's given. It's not like an arbitrary constant. It's just a parameter of equation. Now we are going to raise it to the power of e. So we have absolute value of y, e to the power of at plus c, which we can write down as c to the power of at. And then we can kind of, here c is positive, but if we drop absolute value here, we are going to get like solution e to the power of at. Well, you see that my solution looks like exponential, right, for this equation. Maybe this equation is going to have also exponential solution. What is another reason to look for exponential solution? Imagine that it's not exponential. Imagine that it's some other function. For example, ln. Just like I'm taking any function, but like let's consider solution y equals, I don't know, some constant by ln of t. First derivative of this equation is going to be what? C over t. And the second derivative is going to be minus c over t squared. If you plug everything in to equation like this, or even more general equation with coefficients ABC, you're going to see that you're going to deal with three separate functions. And there is no way to find a constant or variation of constants which is going to turn it into like 0. So it's very natural to look for a solution which is not changing while you are differentiating it, because you are going to add these all derivatives together and eventually they're supposed to go to 0. So maybe you should look for a function which does not change much when you differentiate it. And that's a good function which is like exponential. All other functions are going to change. Imagine that you consider, for example, tangent is going to become like what? Derivative of tangent is secant square, and derivative of secant square is secant square tangent. So again, every other function is turning into something else, and it's going to be very hard to compensate this something else into equation, because some of this is not going to be 0, no way, right? They're all three different functions. Well, now when I kind of explained a little bit why we need to consider exponential solution, we can just try exponential solution into our equation. So imagine that we are searching for a solution y of t equals c e to the power of rt, and c and r are the constants which are supposed to be defined while we are solving it. I'm going to find the first derivative, and first derivative is going to be c. C is a constant, derivative of exponential function is exponential function itself, and multiplied by r, derivative of rt. The second derivative is c ERT. We copy this r from the first derivative and differentiate exponential function one more time. We get r squared. Now what I'm going to do, I'm going to plug in all derivative, first function, derivative, and the second derivative into my original equation with arbitrary coefficients. We're not going to solve this particular one in the beginning, just I'm going to show you that it's possible to solve this. So what is going to happen if I plug everything in? Well, a, the coefficient of second derivative, then second derivative. I'm going to write down c e to the power of rt by r squared plus b c e to the power of rt multiplied by r, and the last one is c. I'm going to put big C, the constant of the equation, and this c is different, this c is coming from the equation, e to the power of rt, right, there is no r, and it's supposed to be equal to 0. What I'm going to do now, guys, I'm going to separate or take outside of parentheses a common factor c from all of them and e to the power of rt. What do I have in parentheses? A r squared plus b r plus c equals to 0. Well, we do remember that exponential function e to the power of rt is never equal to 0, right? Exponential function usually looks like this, never crosses x-axis. So I'm going to write down never equals to 0. Constant is also not equal to 0. Why? It's not bad for the constant to be equal to 0, but imagine that constant over here is equal to 0. Then solution is going to be y equals 0. Is it actually going to solve our initial equation? Well, just plug in. Y equals 0, derivative of 0 is 0 and 0. So 0 is solution of this equation. But it's a trivial solution. Trivial solution means that boring, not interesting. And y equals 0 is going to be solution of any equation of second order with arbitrary coefficient, homogeneous. So we're not going to worry about this. So constant is not equal to 0, exponential factor is not equal to 0. The only chance for this to be equal to 0 for this expression is to make 0 ar squared plus br plus c equals 0. Well, because we want to have a product equals to 0. This equation of second order is called characteristic equation. And for this equation, we actually can, if somebody gives us coefficients a, b, c for the equation, we can find out, right? We just can solve it. That's just a quadratic equation. Let me see if this can still see it on the screen. So I'm going to write down a general formula. I don't want to kind of give solutions. So it's plus minus square root of b squared minus 4ac minus b divided over 2a, right? Two solutions of second order equation. Now, what are the possibilities for two solutions? We know from algebra that there are three different cases for roots of this equation. Case number 1, there can be two real roots, r1 not equal to r2 real. Case number 2, both roots can be equal to each other. When does it happen? When this expression under the square root is equal to 0, right? When expression under the square root is equal to 0, then it's going to be plus minus 0 minus b over 2a. When the coefficients are equal, when the roots are equal to each other, we have a repeated root. And the last case, we can have this expression under the square root negative, and then we are going to have two complex conjugate solutions, right? Two complex conjugate solution, R1 and R2 complex conjugates. Well, each of these three cases is going to produce its own solution, depending on like which case we are. Today we are going to work with number 1, when we have two real different roots. And next lecture is going to be about two repeated roots, and next lecture is going to be about two complex conjugate solutions. Okay, well, because we explained all the theory already, we can move to actual solving of actual equation. Let me remove this page. And I'll put one more, make sure that everything is visible. Straighten it. Yeah, looks like it's a straight one, right? So let's consider, well, let's write down like example number 1, second derivative plus 5 first derivative plus 6y equals to 0, y of 0 equals 2, and y prime of 0 equals 3. So this is initial value problem. Initial value problem equation is given, constant coefficients, and function is given at point 0 and derivative is given at point 0. Why do we have two initial conditions? Because it's a second order equation, right? Well, let's try to solve it. So first we are going to write down that we are searching for a solution as e to the power of rt multiplied by a constant, right? Well, because I already did the differentiation, I know what is going to come out, and my second order equation is going to be like, instead of the second derivative, I put r squared, instead of the first derivative, I put r, and instead of function, I put nothing to get my quadratic equation. If you wish, you can differentiate it one more time, plug it in, exclude that constant is equal to 0 and exponential factor is equal to 0. You are going to get the very same equation. The fast way to get it is just like, okay, convert the second derivative into r squared, convert the first derivative into r, and convert 0 derivative or the function itself into nothing. Well, what are the solutions here? Let's just kind of calculate them using the formula r1, r2, plus minus a square root of 25, right? Minus 4 multiplied by 6, right? A is equal to 1 by 4 by 6. Well, I can write down 1, 2 here. Minus 5 and divided over 2. Well, it's supposed to be 2a, but 2 multiplied by 1 is 2. Okay, we do have 25 minus 24, which is 1, so plus minus 1, minus 5 over 2. So we have plus 1 minus 5 is negative 4, over 2 is negative 2. And minus 1 minus 5 is minus 6 over 2 is negative 3. So my two solutions are negative 2 and 3. Negative 3. Well, what are they going to produce? They're going to produce for me two solutions, actually, right? I found two different r's. Solution number 1, r1t, and solution number 2. And for me, they are going to be c1 e to the power of negative 2t and y2 equals c2 e to the power of negative 3t. Now the question is, which one should I choose? Both are going to satisfy equation. If you just take this one, remember, you plug it in, because it's a root of this equation, characteristic equation is going to turn, minus 2 is going to turn it into 0. It's just minus 2 squared, it's 4. Minus 2 multiplied by 5, it's 10. So 4 minus 10, it's negative 6 plus 6, 0. So both are going to solve this differential equation. Which one should we choose? Well, let's choose solution number 1, like the first one, y1. And use initial conditions on it. And find C1 from initial conditions. So what I have, y of 0 equals 2. So I'm going to write down y1 of 0. What is y1 of 0? It's just like if I plug in 0 here, I'm going to just get c1 equals 2. y1 prime of 0, which is going to be what? c1 by negative 2 derivative. Well, e to the power of 0, which is 1, it's supposed to be equal 3. And what I have two conditions on the constant c1. c1 equals 2, and on the other hand, c1 supposed to be equal minus 3 over 2, which is actually a contradiction, right? c1 cannot be equal to both things. So if you consider just one function, you cannot satisfy two initial conditions. System is overdefined. You have just one variable and two different equations. So how do we kind of resolve this? Well, to solve two equations, which are going to be produced by two initial conditions, we'll need two variables. Where do we get the second one? Well, from function y2, right? Before we do this, before I start kind of using y2 as my second solution and add it to the first solution, I want to verify this fact a little bit. I'm going to show that y of t, which is y1 of t plus y2 of t, is also solution of differential equation. Well, guys, I actually don't know. I can verify it not for just equation with constant coefficients, but I can verify it for more general equation with P and Q. That's going to be always working. Maybe I should do this for constant coefficients first and then verify it for like more general form. Well, let's consider constant coefficients. So y prime of t equals y1 prime plus y2 prime, right? y2 prime of t equals y1 2 prime plus y2 2 prime. Because equation is linear by the nature of the equation, we are going to have a very nice a y1 second derivative y2 second derivative plus b first derivative y2 first derivative plus c y1 plus y2. Question is it going to be 0? Because, well, this y1 and y2 are solutions. Is the sum of them is going to be a solution? Well, I'm going to separate y1 function from y2, and I'm going to write them down like together. Sorry, first derivative, just first derivative. So this is my equation, and because y1 is a solution of my equation, a y second derivative plus b y first derivative plus y, because y1 is a solution, it turns this equation into 0. So this expression is equal to 0. y2 is also a solution of the very same equation, so it's going to turn it into 0. So the sum is going to be 0. Generally, it's going to be even true for more general equation, which we considered in the beginning, linear equation with non-constant coefficients, and eventually we are going to consider it. But for right now, because we are dealing with constant coefficients, let's just like know this fact that the sum is going to be also a solution. How about the difference? Is the difference going to be a solution? Well, just imagine that you put a minus here, and minus here. What we are going to have? Well, we are going to have this one minus, minus, minus. Well, 0 and minus 0 is still 0. So the difference is a solution too. Actually, if you multiply this solution by any arbitrary constant and this solution by another arbitrary constant, you are going to get these constants in front of the whole solution here and in front of the whole solution here. If it's a solution, it's going to turn into 0, the whole equation, and you multiply it by a constant, it's still going to be 0. So sum of solutions, difference of solutions, or I would say linear combination of two solutions is going to be a solution. And linear combination is sum where you multiply each by arbitrary constant. Okay? Now, how is it going to help us? It's going to help us because we can solve now initial value problem. Because we have a solution which consists out of y1 plus y2, and I'm going to write it down c1e to the power of negative 2t plus c2e to the power of negative 3t, and I'm going to plug in y of 0 equals 2, and what I'm going to have, if I plug in 0 here and 0 here, I'm going to have c1 plus c2, and y prime of 0 equals 3, and prime is minus 2c1, and exponential is going to give me just 1, and minus 3c2, and that's a system of two variables, c1, c2. They are constants, but for the system they are unknowns, right? And equals to two different numbers, we can solve it. So what I'm going to do, I think I'm going to multiply first equation by 2, and add it to the second equation. So I have 4 plus 3, which is 7. And if I add 2 and minus 2, it's 0. 2 and minus 3, it's minus c2. So c2 equals minus 7. Now I think I'm going to multiply first equation by 3 and again add it to the second equation. Multiplying by 3 here it's 6 plus 3 it's 9, right? 3 here is going to cancel with this term. This 3 and 3 are going to cancel because that's positive, that's negative. 3 here is going to be 3 minus 2, which is going to give me just C1. So C1 equals 9. What is going to be my solution of initial value problem? Y equals 9 e to the power of negative 2t minus 7 e to the power of negative 3t. So this function solves equation plus satisfies initial value problem. And that's a solution. Well, more generally, guys, if somebody does not give you initial value problem, you are going to write down both solutions and write down your final solution as a sum. Sum is going to be called a general solution. So this is solution of initial value problem. Now, if you write down your solution like this, C1 e to the power of negative 2t plus C2 e to the power of negative 3t. Leave the constants unknown because no one set up initial value problem. We're going to call this general solution. General solution of differential equation. Okay, maybe we should do a couple of more examples. Let me see. Yeah, a couple of more examples. So guys, I'm going to give you 2 questions and ask you to solve them yourself. And of course, I'm going to provide solution, but like after a while. So you can stop the video and compare then your solution with mine. So self. Problem A. Well, I'm going to ask something simple. For second derivative y minus 9y equals 0. And here I'm asking find the general solution. So undetermined constants. And problem B, second derivative plus 4, first derivative plus 3, the function equals to 0. And y of 0 equals 2, and y prime of 0 equals negative 1. Solve initial value problem. Solve initial value problem. Yeah, okay. So I'm going to count to 3, and you can stop your video and try to solve these problems on your own, and I'm going to produce solutions. Okay, so 1, 2, 3. Let's start with problem A. Let me put solutions. Well, for second derivative minus 9y, characteristic equation is 4r squared minus 9 equals to 0. Happens sometimes, so solve it for r. It's plus minus square root of 9 over 4, or r equals 3 over 2, and I'm going to put plus minus. So there are 2 r's. So solution y equals c1 e to the power of 3 over 2t plus c2 e to the power of negative 3 over 2t. 2 solutions, very easy, general solution. No initial conditions are given, so you can keep your solution like this. B, a little bit more complicated. Second derivative plus 4 first derivative plus 3y equals 0. Initial conditions, y of 0 equals 2 and y prime of 0 equals negative 1. Well, characteristic equation, r squared plus 4r plus 3 equals 0. Well, maybe you just can look at this equation and guess about solutions. R1 equals, let's say, 3, and R2 equals, let's say, 1. How about this? Now I'm going to check it. The product is equal to 3. The sum is equal to 4. The only one little difference that they're supposed to be with minuses, right? I mean, if you factor it, that's like minus 1 or minus 3, right? plus 3, sorry, plus 1 plus 3 equals to 0. And the roots are minus 1 and minus 3. Okay, so general solution is going to look like this. Y equals C1 e to the power of negative 3t plus C2 e to the power of negative t. Now I'm going to satisfy initial conditions. Y of 0 equals 2, and 0 here and 0 here are going to turn the exponential function into 1, this one into 1, and C1 plus C2. By the way, guys, why do we always set up initial conditions at 0? It's not difficult to set up initial condition at 1 or at 2 or at 3, but if you plug in 1 here, it's going to give you exponential function, for example, e to the power of negative 3. It's just harder to calculate if you have it. But normally, initial conditions are absolutely not necessarily supposed to be set at 0. Well, we do it at 0 to make it a little bit easier, but they can actually be at any point t. So y prime of 0, which equals to negative 1, well, we differentiate the first one, we get negative 3c1. Differentiate the second one, negative c2. And we do have two equations, two unknowns. What I'm going to do, I'm going to add first equation and second, kill c2 and have negative c1, negative 2c1 actually, equals 1, right? So c1 equals negative 1 half. Now I'm going to multiply equation number 1 by 3. I'm going to get 6 minus 1, which is 5, right? Here, 3c1 minus 3c1 cancel each other. 3c2 minus c2, it's 2c2. Is going to give me c2 equals 5 over 2. Now I'm just going to write down my general solution. Solution of initial value problem. Y of t equals negative 1 over 2 e to the power of negative 3t plus 5 over 2 e to the power of negative t. Well, I'm going to use GeoGebra to produce a graph of a solution just for you to see like how general a solution of this equation is going to look. It's going to be on the next slide. I cannot kind of teach on paper and then teach on the computer at the same time. So I'm going to produce it and then attach it to the video. Well, I think that's all. So just do the homework and practice a little bit. I don't think that you'll need too many problems to kind of learn how to solve second order differential equations for R and then find the initial conditions. So basically here we solve one quadratic equation, find the roots. Second, we solve two linear equations and find the constants. That's maximum. Minimum is just to solve quadratic equation. Okay, that's all for this section 3.1.